Hello, this is David Kein and my partner Dustin O'Connell, and this is our video for the take-home midterm. Starting off with problem number 2.
So for problem number 2, we are given that a non-isothermal batch reactor can be described by the following equations. Our first differential equation is that the change of concentration with respect to time, and the second differential equation is the change of temperature with respect to time, where the temperature is in degrees Celsius and the concentration is in g moles per liter. A is a regression constant that is always 1000. Our initial temperature is 16 degrees Celsius when our concentration is 1 g mole per liter, and T sub B is 20 degrees Celsius.
In portion A of number 2, we are trying to solve the two differential equations above using the two different methods that we learned in class, the Euler method and the predictor corrector method. We will be using a time interval of 5 hours with a time step of 0.1 hour per step. We will be plotting the two methods in one figure, one for concentration, one for temperature, and then we will take the absolute difference of each option for each equation to determine the difference between the two. So here is the beginning of our script for 2A. We took the script from the differential code given in the course website and changed the limits and the time steps and initial conditions up here. Copied the script, changed the equation to the first equation, which is the concentration equation, and set the initial condition here. Change the segment and continued onward. Then we started the for loops for each method. I can't scroll. Here we go. For the Euler method, to start off for the concentration for the Euler method, which we use the script from the differential code using the function f, which is found on this tab here. Simple. Then continued on with the Euler method for the temperature equation, which we use equation G found on this tab. Continue on with the predictor corrector method for the concentration and the temperature once again. Set it to an interval of D, which is what the time was, 0 to 5 with an interval of 0.1. Set the subplots for each of the four, which is the concentration method comparison, the temperature method comparison, then the final two are the concentration difference between the methods of each. If we run the equation, or the script, here are our four charts. Out of screen a little bit there. But as you can see, the Euler and predictor methods are very close. The differences, absolute value differences, change quite a bit. For the temperature method comparison, we determined that we most likely did something wrong, considering we're getting values to 10 to the 184th temperature all the way once we get up near 5 hours, which cannot be correct. But we cannot figure out how to change that, which would therefore screw up our absolute difference as well.
Now that we have completed part A to the best of our ability, we will move on to part B. In part B, we will attempt to write a script using a while loop to find the required delta T to make the difference between the Euler and the predictor corrector method in terms of temperature below a certain standard. We will be decreasing the delta T within the while loop by 0.001 each time from 0.1, and ultimately we will be trying to find the delta T that will make the error smaller than 10 to the negative third. And when I said E, I actually meant the difference between the values of the Euler method and the predictor corrector method, the absolute values of those. I just said error because in certain while loop examples we will use error terms instead of the differences. So we started with an initial difference of 1. We could have set this to other values, but we just chose 1. So we did a while loop in which while our difference is greater than E, it will continue to run, and our E value is 0.001. So we started off by putting in our initial conditions, and then we made 2 empty vectors that will be later filled in with values, right here, our C and our T vectors. We are setting the first value in our C vector to be the initial concentration of 1, and then we are setting the first value of our temperature vector to be the initial temperature, which is 16 degrees Celsius. Within our while loop, we will then set up a for loop which will fill in the rest of the values in the concentration and temperature vectors for each running of the while loop. So basically we have typed in our equations, and each ith term will be filled in for the concentration and the temperature using these two equations. The concentration vector and the temperature vector that we have just created will be used later on to find the mean difference between all the values in the Euler and the predictor corrector method. These vectors will represent the Euler method. Our dt has been defined in our command window already, and our tb has also been defined in that window from when we ran our first code. Once we have typed the code for our Euler method section of the while loop, we are going to make a for loop for the predictor corrector method. We have t be a vector from 0 to 5 split up in increments of dt, which is going to be a changing value for each while loop. So we again set up a couple of empty vectors for the concentration and the temperature for the predictor corrector method, as we did for the other for loop that we've done. We again put in our initial conditions, which we have at the top of our code, and we use the basic format for the predictor corrector method that can be found on the slides from lecture, and we insert that into our for loop. We end our for loop, and then finally we take the difference, or we find our difference, which is the mean of our absolute value between the difference of the Euler method and the predictor corrector values, which is divided by the predictor corrector values.
Lastly, before we close our while loop, we want to change our dt value by subtracting 0.001 from it each time the while loop is run, and the while loop will end when the dt value, or the difference value, is less than 0.001. So we will now just run and display our difference value our mean difference value that we get. Change the file here, and it shows that we get a value of negative 10.62. We are not completely sure whether this is a correct answer or not, but it's the answer we got. So, and that concludes our take-home midterm video. Thanks for listening.